Hello there, and welcome back to the Sleep Well channel. I'm so glad you've chosen to spend this quiet time with us. The day is behind you now with all its noise and hurry. This moment is for something different. A time for stillness, for wonder, and for letting your mind drift into the deepest and most peaceful questions imaginable. Tonight, our journey takes us beyond the familiar stars and galaxies, beyond even the fabric of space and time, into the heart of physics itself. We won't be solving equations or memorizing laws. Instead, we'll be floating through the great unknowns, the cosmic whispers and gentle paradoxes that scientists have yet to answer. These questions are not problems to be solved tonight. They are invitations to wonder, doorways into a universe far stranger and more beautiful than we can comprehend. You don't need to do anything now. There are no answers to find, no puzzles to piece together. You have nothing to do but rest. Let your body grow heavy against the surface beneath you. Let your breath find its own slow, quiet rhythm. In and out. Feel the edges of the day begin to soften. The thoughts of tomorrow gently drifting away. Because tonight, we are not here to think, but to dream. We are here to listen to the questions the universe is asking itself. If these quiet journeys into wonder help you find rest, consider gently liking and subscribing. It helps other sleepy souls find their way to this little corner of the cosmos, too. One at a time, now. If you're ready, let your mind grow still, and let's begin. Perhaps the deepest question of all is also the simplest. Why is there something instead of nothing? Before the stars ignited, before atoms formed, before the Big Bang itself, there was. What science can trace the story of the universe back almost to its first instant, but it cannot explain the page on which that story is written. It cannot explain existence itself. This is not a failure of physics, but the place where physics meets philosophy. The quiet, unwritten preface to the cosmic story. Some theories whisper possibilities. They suggest that what we call nothing, a perfect vacuum, is not truly empty. Even in the blackest void, quantum physics tells us that energy shimmers. Tiny particles flicker into existence and vanish in an instant, a constant restless hum beneath the silence. Is nothingness itself unstable, like a silence so deep it must eventually break? Perhaps the universe we know is simply one of these fluctuations, a flicker that for some reason lasted. Other ideas: imagine a vast multiverse where countless universes bubble into being, each a roll of the cosmic dice. We simply find ourselves in one that exists because, well, we couldn't ask the question in a universe that didn't. This is a kind of cosmic lottery, but it only pushes the question back. Why does the multiverse itself exist? There is no experiment we can run, no telescope we can build that can look outside of existence to see why it is here. The question remains suspended in the space between atoms and the void between galaxies. It is the quiet hum beneath all other sounds, the foundation on which everything you know is built. The simple, astonishing fact that you are here at all, resting in a universe that did not have to be. And from that fundamental mystery of existence, we drift to its first known moment, the beginning of everything we can measure. We call it the Big Bang. But what or who lit the fuse? Cosmology tells us a beautiful story. Nearly 14 billion years ago, The entire observable universe was compressed into a single point of impossible heat and light. It wasn't an explosion in space. It was the unfolding of space itself. In a fraction of a second, the universe began to expand, to cool, and to set in motion the laws that would one day give rise to galaxies, stars, and your own quiet breath in this very moment. We can see the echoes of this beginning. We can measure the ancient light, the cosmic microwave background, which is like the faint warmth left over from that first cosmic ember. We can see the galaxies still rushing away from each other, carried on the expanding currents of space-time. But our story always begins a moment after the beginning. What came before? What triggered it? Our laws of physics break down at that first instant. Time itself may have begun there, making the word before meaningless. Some theories suggest the Big Bang was a quantum fluctuation, a random tremor in a pre-existing state that gave birth to our reality. Others imagine a cyclical universe, one that expands, collapses, and is reborn again and again, with our Big Bang being just one of countless breaths. In this view, the universe has no beginning and no end, only an endless rhythm of creation and dissolution. We can only stand at the edge of that mystery, gazing back at the faint light from a time we cannot truly touch. The first cause, the spark that set the cosmos in motion, remains hidden from us. It is a question written not in light, but in the silence that preceded light. A gentle reminder that every story has a first line, and the universe's first line is one we have not yet learned to read. Floating within this new universe is the river of time. We feel it constantly, a gentle current carrying us from yesterday into tomorrow. A broken glass does not reassemble itself. We remember the past, but not the future. Yet when we look at the fundamental laws of physics, the equations that govern particles and forces, they seem to be indifferent to time's direction. At the smallest scales, most physical processes could run forwards or backwards without violating any rules. So why does our universe have such a clear and unwavering arrow of time? Why does everything move from order to disorder? A process called entropy. The most common answer is that the universe began in a state of incredibly low entropy, a state of perfect, simple order. Like a perfectly wound clock at the beginning of time, it has been unwinding ever since. The increasing disorder, the steady march of entropy, is what we perceive as the forward flow of time. Every moment, the clock ticks down, and the universe becomes a little more chaotic, a little more spread out. But this, too, leads to a deeper question. Why did the universe begin in such a pristine, ordered state in the first place? Out of all the possible ways the universe could have started, it began in one that was exceptionally special, exceptionally orderly. Was it a random chance? Or does it hint at a deeper principle we don't yet understand? A law governing the beginning of laws. When you rest here feeling one moment slip into the next, you are experiencing one of the greatest unsolved mysteries. You are floating on a current whose source is unknown. A one-way river flowing through a cosmos that at its core does not seem to care which way the water runs. The arrow of time is not just a law of physics. It is the very rhythm of your life, a gentle, constant, and profoundly mysterious pulse. And this question of time's direction opens into an even deeper one. Is the universe deterministic, or is it fundamentally random? Imagine the cosmos as a great and intricate machine. If you knew the precise position and momentum of every single particle at one moment, could you in theory calculate the entire future? This is the idea of determinism, a universe where every effect has a cause, and the future is simply the playing out of initial conditions. In this view, free will might be an illusion, a beautiful story we tell ourselves, while the script of the cosmos was written at the very beginning. Everything from a star's explosion to a quiet thought drifting through your mind was set in motion long ago. But quantum mechanics, the physics of the very small, tells a different story. It suggests that at the deepest level, reality is not fixed, but probabilistic. A particle, like an electron, doesn't have a definite position until it is measured. Instead, it exists in a cloud of possibilities. When a radioactive atom will decay is not predetermined. It is a matter of pure chance. Einstein famously disliked this idea, stating that God does not play dice with the universe. He believed there must be hidden variables, deeper rules we just haven't discovered yet, that would restore a sense of order and cause. Yet experiment after experiment has confirmed the strange probabilistic nature of the quantum world. There appears to be a genuine randomness woven into the fabric of reality. So, which is it? Does the universe unfold like a perfect clockwork mechanism? Or does it make itself up as it goes along with moments of pure, uncaused chance? Perhaps both are true in their own realms. The large-scale universe of planets and galaxies might behave with predictable clockwork grace, while the tiny subatomic world dances to a rhythm of probability. This is not a question you need to answer. Just feel the gentle possibility of it. Your own consciousness, your thoughts and feelings might be part of an ancient predetermined script, or they might be a truly new creation, born of quantum chance in this very moment. Either way, the story is beautiful. Either way, it is a mystery. And in that mystery, there is a kind of peace. As we drift from the nature of time and existence itself, our journey now takes us into the vast, unseen parts of the cosmos. The universe we see with our telescopes, the glowing stars, the swirling nebulae, the great spirals of galaxies, is only a tiny fraction of what is actually there. Most of the universe is hidden from us, cloaked in a kind of cosmic shadow. And the greatest of these shadows is called dark matter. What is it? When astronomers look at a spinning galaxy, they see something that shouldn't be possible. The stars on the outer edges are moving far too quickly. According to our understanding of gravity based on the visible stars and gas, those outer stars should be flung off into the void like children letting go of a fast spinning carousel. But they aren't. They remain in their orbits held in place by a gravitational grip far stronger than what we can account for. The conclusion is inescapable. There must be more mass, much more that we simply cannot see. This invisible substance is dark matter. It doesn't shine. It doesn't reflect light. And it doesn't seem to interact with ordinary matter in any way except through gravity. It is the invisible scaffolding of the cosmos, an unseen framework that holds galaxies together, that bends the path of starlight, and that guided the formation of the great cosmic web of structures we see today. It outweighs all the visible matter in the universe by more than 5 to 1. But what is it made of? This is where the mystery deepens. For decades, scientists have searched for the particles that might make up this cosmic shadow. One leading idea is a type of particle called a WIMP, or a weakly interacting massive particle. These hypothetical particles would be heavy, but would pass through ordinary matter almost without a trace, like ghosts. Billions of them might be streaming through your body, through the very earth beneath you at this very moment, and you would never feel a thing. To search for them, scientists have built enormous detectors deep underground, shielded from other cosmic radiation, hoping to catch the whisper of a single WIMP colliding with a single atom. So far, the silence has been profound. Another possibility is a particle called an action, which would be incredibly light and even more elusive. Or perhaps dark matter isn't a particle at all. Some theories suggest it could be made of primordial black holes, tiny black holes formed in the fiery moments after the Big Bang, long before the first stars. These ancient relics would drift through space, their gravity shaping the cosmos, but their presence known only by the way they pull on the things we can see. The search continues in deep mines and with powerful telescopes for a glimpse into this hidden world. For now, dark matter remains a gentle, persistent question mark hanging over the universe. It is a quiet reminder that the most important structures in the cosmos may be the ones we cannot see, held together by a force we can feel, but a substance we have not yet found. And just as there is an unseen matter holding the universe together, there appears to be an unseen energy pushing it apart. We call it dark energy. For much of the 20th century, astronomers assumed the expansion of the universe, which began with the Big Bang, must be slowing down. After all, gravity is a force of attraction. Every galaxy should be gently pulling on every other galaxy, acting like a cosmic brake on the expansion. But in the late 1990s, observations of distant supernovae revealed something astonishing, something that no one expected. The expansion of the universe is not slowing down. It is accelerating. Something is acting against gravity, pushing galaxies away from each other at an ever-increasing rate. This mysterious influence, this gentle but relentless push, is what we call dark energy. It doesn't seem to be a substance like dark matter, but rather a property of space-time itself, a kind of energy inherent in the vacuum of empty space. And its influence is immense. Dark energy is thought to make up nearly 70% of the total energy content of the universe. So what is it? One idea is that it is the cosmological constant, a concept Einstein himself proposed and later called his biggest blunder. He imagined a kind of anti-gravity force that would keep a static universe from collapsing. When it was discovered the universe was expanding, he abandoned the idea. But perhaps he was right after all. Not about a static universe, but about an energy embedded in the fabric of space. This vacuum energy might come from the fleeting quantum particles that flicker in and out of existence in empty space. But here, another mystery arises. When physicists try to calculate how much vacuum energy there should be based on quantum theory, they get a number that is astronomically, incomprehensibly larger than what we observe. The discrepancy is so vast a one, followed by 120 zeros, that it has been called the worst theoretical prediction in the history of physics. Why is the observed energy of the vacuum so incredibly small, so perfectly tuned to allow galaxies and stars to form? No one knows. This puzzle, the cosmological constant problem, is one of the deepest in all of science. Perhaps dark energy is not constant at all. It could be a dynamic field, which some have nicknamed quintessence, that changes over time and space. If so, its strength might grow or fade in the distant future, leading to very different cosmic endings. The nature of dark energy will determine the ultimate fate of the universe. If it remains constant, galaxies will continue to accelerate away from each other until our own galaxy is left as a lonely island in an endless empty void. If it grows stronger, it could one day lead to a big rip, where the force becomes so powerful it tears apart galaxies, then stars, then planets, and finally atoms themselves. For now, dark energy is simply a name for our ignorance. It is the unseen breath of the cosmos, a force that is gently, inexorably stretching the universe into a future we can only guess at. A quiet, invisible current, carrying everything we know farther and farther apart. We have drifted through the great shadows of dark matter and dark energy, the unseen components that dominate the cosmos. Now, our journey turns inward to the very fabric of reality itself. We question not just what fills the universe, but what the universe is. What is space-time made of? Einstein's theory of general relativity gave us a new way to imagine the universe. He showed us that space and time are not a fixed, rigid stage on which events unfold. Instead, they are a dynamic, flexible fabric space-time that can be bent, warped, and curved by mass and energy. A planet doesn't orbit the sun because it is being pulled by an invisible rope of gravity. It orbits because it is following a straight line through the curved space-time created by the sun's mass, like a marble rolling around a dip in a stretched sheet. This picture of a smooth, continuous fabric works perfectly at the scale of stars and galaxies. But when we try to zoom in to the impossibly small scales governed by quantum mechanics, the picture grows fuzzy. Quantum theory suggests that everything at its most fundamental level should be grainy and uncertain. Energy comes in discrete packets or quanta. So, shouldn't space and time be the same? This leads to a profound question. Is space-time smooth and continuous like a perfect silk cloth that can be divided forever? Or is it pixelated and discrete like a digital image made of tiny, indivisible units? Some theories of quantum gravity propose that there is a smallest possible length, known as the Planck length. It is a distance so unimaginably tiny that our minds can barely grasp it, billions of times smaller than a single proton. At this scale, the smooth fabric of space-time might dissolve into a shimmering quantum foam. A place where space and time are no longer well-defined, but fluctuate in a haze of probability. In this view, our reality is like a high-resolution screen. From a distance, it looks perfectly smooth, but up close, you can see the individual pixels that make up the image. If this is true, it would mean that you can't divide space forever. There is a fundamental graininess to the universe. We don't yet have the technology to probe these scales directly, so the question remains open. But it is a beautiful one. to hold in your mind as you rest. The very space you are in the air in the room, the distance between your hand and your face. Is it an infinitely smooth expanse, or is it a tapestry woven from an incredible number of tiny finite threads? The stage of the universe may not be what it seems. And on this stage, 4 fundamental forces play out their roles. The strong and weak nuclear forces that govern atoms, electromagnetism, that governs light and chemistry and gravity. But one of these forces is an outlier. One of them is mysteriously, almost absurdly weak. Why is gravity so much feebler than the other forces? This is known as the hierarchy problem, and it is one of the most puzzling aspects of modern physics. Consider this: the electromagnetic force is so powerful that a tiny magnet on your refrigerator can defy the gravitational pull of the entire Earth. The force holding a single atom together is vastly stronger than the gravitational force between you and the person next to you. Gravity only becomes noticeable when you have objects with enormous mass like planets or stars. Why? This immense discrepancy. The other 3 forces operate with a certain comparable strength, but gravity is trillions of times weaker. It's as if it belongs to a different universe entirely. Physicists have proposed several intriguing, though unproven explanations. One of the most captivating is the idea of extra dimensions. We experience the world in 3 dimensions of space length, width, and height plus 1 of time. But what if there are more? String theory, for example, suggests there could be as many as 10 or 11 dimensions. Most of these would be tiny, curled up so small that we can never perceive them. In this picture, the other forces might be confined to our familiar 3-dimensional brain or membrane of space-time. But gravity, being a property of space-time itself, might be able to leak out into these hidden extra dimensions. If this were true, the gravity we experience would only be a faint echo of its true strength, diluted as it spreads across all the dimensions. This would explain its apparent weakness in our world. Another possibility is that gravity only seems weak to us. Perhaps its true strength is just as powerful as the other forces, but it only reveals itself at incredibly high energies or small distances in ways we have not yet been able to test. The weakness of gravity is not just a curiosity, it is essential for our existence. If gravity were even a little bit stronger, stars would burn out much faster, their immense pressure overwhelming them. Planets might not be able to form stable orbits. The universe as we know it would be a very different and likely uninhabitable place. So as you feel the gentle, persistent pull of Earth's gravity holding you in place, remember the mystery it holds. It is a force strong enough to hold oceans and shape galaxies, yet so faint it can be overcome by a child's toy. A quiet, constant force whose true nature and whose strange relationship with its sibling forces remains one of the deepest secrets of the cosmos. It is a whisper where the other forces shout. And as we ponder gravity, we arrive at the greatest challenge in modern physics, the search for a theory of quantum gravity. How does gravity work at the quantum level? We have 2 incredibly successful theories that describe the universe. General relativity, which explains gravity, and the cosmos of the large planets, stars, galaxies, and the expansion of space. And quantum mechanics, which explains the world of the small particles, atoms, and the other 3 fundamental forces. Both theories have been tested to extraordinary precision, and both work perfectly in their own domains. But they refuse to work together when we try to describe situations where both theories must apply, like at the center of a black hole, where enormous mass is crushed into a tiny space, or in the first moments of the Big Bang, the mathematics breaks down. The equations produce nonsensical infinities. It's as if the two great languages of physics are speaking about different universes. The search for a theory of quantum gravity is the quest to find a single, deeper language that can unite these two pillars of science. A theory of everything that can describe all the forces of nature within one consistent framework. One of the leading candidates is string theory, which proposes that the fundamental constituents of reality are not point-like particles, but tiny one-dimensional vibrating strings. Different vibrations of these strings would give rise to all the different particles and forces we see, just as different vibrations of a violin string produce different musical notes. In this view, gravity would be just another note in a grand cosmic symphony. String theory is mathematically beautiful and elegant, but it requires the existence of those extra dimensions we spoke of, and we have not yet found a way to test it experimentally. Another approach is loop quantum gravity, which suggests that space-time itself is quantized, made of tiny discrete loops woven together into a spin network. In this theory, there is no smooth background of space-time. The fabric of reality is built from these fundamental quantum relationships. Whatever the final answer may be, the quest for quantum gravity is about more than just reconciling two theories. It's about understanding the very nature of reality at its most fundamental level. What is space? What is time? And what are the rules that govern them in the places where our current understanding fails? And within this quest lies a simpler question. Do gravitons exist? Just as the electromagnetic force is carried by particles called photons. Physicists theorize that gravity might be carried by a particle called the graviton. These would be massless particles that travel at the speed of light, carrying the force of gravity across space. But because gravity is so weak, gravitons would be incredibly difficult, perhaps impossible to detect directly. Their existence is a key prediction of most theories of quantum gravity. But for now, they remain purely theoretical. You don't need to grasp these complex ideas. Just let the sense of the search wash over you. The quiet, patient effort of thousands of minds trying to listen for a deeper harmony in the universe. A single law that sings of both the falling apple and the orbiting star, of both the quantum leap and the expanding cosmos. A secret melody that may one day unite everything we know. Our journey now takes a turn, leaving behind the vast, sweeping scales of the cosmos and diving into the strange, shimmering world of the very small. We enter the realm of quantum mechanics, a place where our everyday intuition fails, where particles can be waves, and where reality itself seems to depend on how we look at it. And here, we face the most foundational puzzle of all the measurement problem. In the quantum world, before it is observed, a particle, like an electron, doesn't have a definite location. It exists in a superposition, a ghostly state of all possible locations at once described by a mathematical entity called the wave function. It is a cloud of probability. But the moment we measure it, the moment we look this cloud of possibility collapses and the electron appears in one single definite place. Why? Why does the act of observation force reality to choose? This is the measurement problem. What constitutes a measurement? Does it require a conscious observer, a human mind? Or is any interaction with a larger physical system, like a detector, enough to collapse the wave function? This question has puzzled physicists for a century, leading to a host of strange and wonderful interpretations. The most famous, the Copenhagen interpretation, simply accepts that this is how the world works. The act of measurement is a special kind of interaction that bridges the fuzzy quantum world and our solid classical world, but other ideas are more radical. The many worlds interpretation suggests that the wave function never truly collapses. Instead, every time a measurement is made, the universe splits. In one universe, the electron is here. In another, identical universe, it is there. Every possible outcome of every quantum event happens each in its own separate branch of reality. In this view, there is a near infinite number of parallel universes constantly branching off from our own. Another idea, known as pilot wave theory, suggests that particles do have definite positions all along, but they are guided by a hidden pilot wave. We just can't see this underlying layer of reality, so the particle's behavior appears random to us. The measurement problem is not just a philosophical debate. It strikes at the very heart of what reality is. Is the world a fixed, definite thing that we discover? Or is it a fuzzy, probabilistic thing that becomes definite only when we interact with it? The universe seems to behave differently when we're not looking. The moon, as Einstein once quipped, is surely there even when no one is looking at it. But for a quantum particle, the answer is not so clear. It's a profound and gentle mystery. The world you perceive is solid and real, but the quantum foundations upon which it is built may be a shimmering dance of pure potential waiting for a glance to bring it into being. And from this dance, an even stranger connection emerges, one that seems to violate the very limits of space and time. This is quantum entanglement. When two particles are created in a certain way, their properties can become linked or entangled. They become part of a single quantum system, even if they are separated by vast distances. Imagine you have two entangled electrons. One has a property called spin, which can be either up or down. If you measure the spin of one electron and find it is up, you will instantly know with absolute certainty that the spin of the other electron, its entangled twin, is down. This is true no matter how far apart they are. If one is here on Earth and the other is in the Andromeda galaxy, 2.5 million light years away, the connection remains instantaneous. The moment you measure one, the state of the other is determined. Einstein famously called this spooky action at a distance because it seems to suggest that information is traveling faster than the speed of light, which should be impossible. Experiments have confirmed again and again that this spooky connection is real, but it doesn't seem that a signal is being sent. Instead, it's as if the two particles are not separate entities at all. They are two parts of a single, non-local reality. What happens to one is what happens to the other, because in a quantum sense, they are still one. What does this tell us about the nature of space? Does it mean that at the deepest level, our universe is profoundly interconnected that distance itself is an illusion? Or does it point to a deeper layer of reality, a set of hidden variables that coordinate the particle's behavior? We are now harnessing entanglement for new technologies like quantum computing and unhackable communication. We are using the spookiness, even if we don't fully understand it. As you lie here, feel the space in the room around you. It feels empty and still. But the mystery of entanglement suggests that this stillness may be woven with invisible threads, connections that defy distance and link the universe together in ways we are only just beginning to glimpse. It's a quiet, humbling thought that the fabric of reality may be far more interconnected, far more unified than our eyes can ever see. That a particle in a distant star might share a silent, instantaneous bond with a particle right here in this very room. This intricate web of quantum connections has led some physicists to a startling idea. Is the universe a giant quantum computer? A classical computer, like the one in your phone, processes information in bits which can be either a 0 or a 1. A quantum computer, however, uses qubits. A qubit can be a 0, a 1, or both at the same time, thanks to the principle of superposition. This allows a quantum computer to explore a vast number of possibilities simultaneously, making it incredibly powerful for certain types of problems. The idea that the universe itself might be a quantum computer comes from the realization that at its most fundamental level, reality is made not of solid stuff, but of information. A particle's properties, its mass, charge, spin, can be thought of as bits of information. The laws of physics are the program, the set of rules that process this information over time. The evolution of the universe from the Big Bang to this present moment could be seen as one colossal quantum computation. In this view, every interaction between particles, every star that forms every leaf that falls, is a part of this ongoing calculation. The universe is not just a collection of objects. It is a dynamic information processing system. This is a powerful and abstract metaphor, but it helps to reframe our understanding of the cosmos. It suggests that information is not just something we use to describe the universe. It might be what the universe is. You don't need to understand the mechanics of quantum computing. Just let the idea float gently in your mind that the quiet unfolding of the cosmos, the slow turning of the earth, the very firing of the neurons in your brain might all be part of a vast, silent computation. A story being written in the language of quantum information. A story whose outcome is the reality you are experiencing right now. The universe, in this sense, is not just a place. It is a process. It is thinking itself into existence. And in your own quiet thoughts, you are a small but beautiful part of that process. Our journey now leads us away from the shimmering uncertainty of the quantum world and toward the deep, gravitational silence of its most extreme creation, the black hole. These are places where the fabric of space-time is stretched to its breaking point, where gravity is so strong that nothing, not even light, can escape. And at their heart lies a question that touches the limits of our knowledge. What happens inside a black hole? According to Einstein's theory of general relativity, when a massive star collapses under its own gravity, it continues to collapse forever, crushing all of its mass down into a single point of infinite density. This point is called a singularity. It is a place where space and time as we know them cease to exist. A place where our laws of physics break down. Surrounding this singularity is the event horizon, the point of no return. Once anything crosses this boundary, its fate is sealed. All paths lead inward toward the singularity. The gravity is so extreme that it warps space-time into a one-way funnel. But is the singularity real? Or is it just a sign that our theory, general relativity, is incomplete? Many physicists believe that a theory of quantum gravity would smooth out this infinity. At the heart of a black hole, quantum effects might become so powerful that they resist the infinite collapse. Instead of a singularity, there might be a Planck star, an incredibly dense but finite object. Or perhaps space and time themselves transform into something new, something we don't yet have the language to describe. Because nothing can escape from beyond the event horizon, we can never look inside to see what is truly there. The heart of a black hole is the universe's most perfect secret keeper. It is a place of ultimate silence and mystery. As you rest, you can imagine that deep, quiet center, not as a place of destruction, but as a place of transformation. A place where matter and energy are returned to a state beyond our comprehension. A point of stillness at the center of a gravitational storm. And this leads us to one of the most profound paradoxes in modern physics, the black hole information paradox. A fundamental principle of quantum mechanics is that information can never be truly destroyed. The details of any physical system, the properties of all its particles, are always preserved in some form. You can burn a piece of paper, but the information about its atoms is still contained in the smoke and ash, at least in theory. But what happens when something falls into a black hole? The information about all its intricate details seems to fall in with it, vanishing forever from our universe, hidden behind the event horizon. This wasn't a huge problem until the 1970s, when Stephen Hawking made a remarkable discovery. He showed that due to quantum effects near the event horizon, black holes are not completely black. They should emit a faint trickle of radiation, now called Hawking radiation. Over an incredibly long time, this radiation causes the black hole to slowly lose mass and eventually to evaporate completely. So, what happens to the information that fell inside if the black hole evaporates and disappears, and the information is not in the faint radiation it emits? Then the information has been truly destroyed. This would violate the fundamental laws of quantum mechanics. This is the paradox. General relativity says nothing can escape a black hole. Quantum mechanics says information cannot be destroyed. The two theories clash at the event horizon. Physicists have been wrestling with this problem for decades. The solutions are as strange as the problem itself. One idea is that the information isn't inside the black hole at all, but is somehow encoded on the two-dimensional surface of the event horizon like a hologram. When the black hole evaporates, this information is slowly released back into the universe. Another possibility is that black holes don't evaporate completely. They might leave behind a tiny stable remnant that holds all the lost information. Or perhaps, in a more radical view, the information escapes through a wormhole into another universe. The information paradox is more than just a puzzle about black holes. It is a deep clue about the relationship between gravity quantum mechanics and the nature of information itself. It suggests that our understanding of reality is still missing a crucial piece. You don't need to solve the paradox. Just let the question rest gently in your mind. Imagine a single book filled with stories falling into a silent, dark library. Does the story vanish forever when the library fades away? Or is it somehow rewritten into the very light that emanates from it? A story transformed, but never lost. The universe, it seems, does not like to forget. And while most black holes we know of are the remnants of massive stars, there is a possibility that some are much, much older. Do primordial black holes exist? These are hypothetical black holes that would have formed not from collapsing stars, but in the chaotic, ultra-dense conditions of the very early universe, just fractions of a second after the Big Bang. In that fiery state, tiny fluctuations in density could have been so extreme that some regions collapsed directly into black holes. Unlike their stellar cousins, primordial black holes could come in a vast range of sizes. Some might be as massive as a galaxy, while others could be as small as a mountain, or even an atom compressed into an infinitesimal point. We have never definitively detected a primordial black hole, but their existence could solve several cosmic mysteries. If they exist in large numbers, they could be a candidate for the elusive dark matter that holds galaxies together. Their gravity would shape the cosmos, but they would be nearly invisible to our telescopes. The gravitational waves we've detected from merging black holes might in some cases be the sound of these ancient objects colliding. The smallest of these primordial black holes, if they were created, would have been subject to Hawking radiation. Over the age of the universe, the very tiniest ones would have already evaporated, possibly ending their lives in a final flash of high-energy particles. Searches for these flashes have so far come up empty, but the possibility remains. To think of these objects is to imagine a different kind of darkness in the cosmos. Not just the remnants of dead stars, but the fossils of creation itself. Black holes, older than the first light, older than the first atoms, born in the fire of the beginning. They would be silent witnesses to the universe's entire history, drifting through the eons, carrying the memory of a time before stars ever shone. The search for them is a search for the universe's oldest secrets, hidden in the darkest corners of space. As our journey continues, we turn from the gravitational mysteries of black holes to the very substance of the universe itself. We drift back to the beginning, to a time when the cosmos was a sea of pure energy, and ask a question that underpins our very existence. Why did matter win out over antimatter? According to our best physical theories, the Big Bang should have produced matter and antimatter in perfectly equal amounts. For every particle, like a proton, there should have been an antiparticle, an antiproton, with the same mass but opposite charge. But there is a problem with this perfect symmetry. When a particle and its antiparticle meet, they annihilate each other in a flash of pure energy. If the early universe had contained a perfect balance, then as it cooled, every particle would have found its anti-partner, and the entire cosmos would have vanished into a sea of light. There would be no galaxies, no stars, no planets, and no one to wonder why. And yet, here we are. The universe we see is made almost exclusively of matter. Something must have tipped the scales. Somehow, for every billion pairs of matter and antimatter particles that annihilated each other, one single matter particle was left over. This tiny surplus This 1 in a billion asymmetry is what formed everything we know. The stars in the sky, the earth beneath you, your own body, all are made from the leftovers of that great annihilation. But what caused this imbalance? Physicists have discovered that the laws of nature are not perfectly symmetrical. There are subtle differences in how certain particles and antiparticles behave, a phenomenon known as CP violation. This slight favoritism for matter might have been enough to create the tiny surplus needed for a universe to form. However, the asymmetries we have observed so far are not large enough to account for the sheer dominance of matter we see today. There must be some other unknown process, some new physics beyond our current understanding that broke the symmetry in the early universe. Perhaps it involves the decay of a new undiscovered heavy particle, or the strange properties of neutrinos. The mystery of the missing antimatter is one of the most profound in cosmology. It is the question of our own origin. As you rest, you can feel the solidity of the world around you. That solidity is a miracle, a statistical anomaly. You are made of the survivors of a cosmic battle, the fortunate few who did not find a partner in the dance of annihilation. You are the 1 in a billion, and the reason for that good fortune is a secret the universe has not yet shared. And the matter that makes you, that makes everything, has a property we take for granted: mass. But what gives particles their mass? Why do some particles, like the photon, have no mass at all, while others, like the top quark, are incredibly heavy? For decades, this was a central puzzle of the standard model of particle physics. The equations that described the fundamental forces worked beautifully, but only if all the particles were massless. The answer proposed in the 1960s was a new invisible field that permeates the entire universe. We now call it the Higgs field. Imagine this field as a kind of cosmic molasses filling all of space. As particles move through it, they interact with it. Some particles, like photons, don't interact at all and can travel at the speed of light massless. Other particles interact strongly with the field, and this interaction, this drag, is what we perceive as mass. The more a particle interacts with the Higgs field, the heavier it is. This elegant theory remained unproven for nearly 50 years until 2012, when scientists at the Large Hadron Collider announced the discovery of a new particle, the Higgs boson. The Higgs boson is an excitation of the Higgs field, a quantum ripple in that cosmic molasses. Its discovery was a monumental triumph, confirming that the field exists and that it is indeed responsible for giving fundamental particles their mass. But the discovery of the Higgs boson did not solve the mystery completely. It opened a new set of questions. Why does the Higgs field have the particular strength that it does? If it were much stronger or weaker, the masses of particles would be different, and the universe, as we know it, with stable atoms and complex chemistry, could not exist. Why do different particles interact with it so differently, creating the wide range of masses we observe? And is the Higgs field the only source of mass, or are there other more exotic mechanisms at play? The Higgs field is a quiet, constant presence in the universe. It is the reason things have substance, the reason the world feels solid. It is an invisible field that gives weight to reality. And as you feel the gentle weight of your own body, you are feeling the effect of your own atoms interacting with this mysterious universe-spanning field. A silent, unseen force that turns energy into substance. And speaking of mass, one of the most surprising discoveries of recent decades has been that neutrinos have mass. Neutrinos are ghostly particles. They are produced in the hearts of stars, in supernova explosions, and in radioactive decay. They are one of the most abundant particles in the universe, with trillions streaming through your body every second. But they barely interact with anything. A neutrino could travel through a light year of solid lead without hitting a single atom. For a long time, the standard model of particle physics predicted that neutrinos should be massless, just like photons. But in the 1990s, experiments revealed something strange. Neutrinos can change or oscillate from one type or flavor to another as they travel. And according to the laws of quantum mechanics, this oscillation is only possible if neutrinos have mass. It is a tiny amount of mass, far less than any other matter particle, but it is there. And this tiny mass has huge implications. It is the first major crack in the standard model, a clear sign that our most successful theory of particle physics is incomplete. There must be some new physics, some mechanism we don't yet understand that gives neutrinos their mass. What is this mechanism? One idea is a seesaw mechanism, which proposes the existence of a very heavy undiscovered partner to the neutrino. The heavier this partner is, the lighter the neutrino we observe becomes, like two children on a seesaw. Another possibility is that neutrinos are their own antiparticles, a strange property that would set them apart from all other matter particles. The tiny mass of the neutrino might also have played a crucial role in the evolution of the universe, influencing the formation of galaxies, and even helping to explain the mystery of the missing antimatter. The neutrino is a particle of whispers. It is almost nothing, but not quite. Its tiny, unexpected mass is a gentle hint from the universe that our most complete theories are still just chapters in a much larger story. A story whose next page we have not yet turned. Our journey has taken us through the unseen matter and energy that shape our cosmos and into the strange rules of the quantum realm. Now we drift to the very edge of what is knowable, to an idea that is as breathtaking as it is unproven. Does the multiverse exist? The universe we can observe is vast, but it is finite. There is a cosmic horizon, a boundary beyond which light has not had time to reach us since the Big Bang. But what lies beyond that horizon, the simplest assumption is that it's just more of the same, more space, more galaxies stretching on forever. An infinite universe. But some of our most powerful physical theories suggest a stranger possibility that our universe is not the only one. It may be just one bubble in a vast frothing sea of other universes, a multiverse. This idea arises from several different areas of physics. The theory of cosmic inflation, which describes the universe's explosive expansion in its first moments, suggests that this process might be eternal. While inflation stopped in our patch of space, allowing our universe to form, it may continue in other regions, constantly spawning new bubble universes, each with its own Big Bang. String theory also leads to the idea of a multiverse. Its equations allow for a staggering number of possible solutions, perhaps 10 to the power of 500, each describing a universe with different physical laws and constants. Our universe, with its particular set of laws that allow for stars, planets, and life, would be just one possibility among a near-infinite landscape of others. The multiverse could even offer a solution to the many worlds interpretation of quantum mechanics. Instead of the universe splitting every time a quantum measurement is made, perhaps all those parallel realities already exist as separate universes within the multiverse. This is a dizzying concept. To imagine countless other realities, some perhaps similar to our own, others so alien they would be unrecognizable, with different forces, different dimensions, different kinds of matter. But there is a profound problem. If these other universes exist, can we ever detect them? By their very nature, they are separate from our own space-time. No signal, no light, no information can cross the void between them. This makes the multiverse a deeply controversial idea in science. A theory that cannot be tested may be closer to philosophy than physics. And yet, the idea persists because it offers an elegant, if unsettling, explanation for some of the deepest mysteries of our own cosmos, like the fine-tuning of the physical constants. As you lie here, you don't need to believe in the multiverse. Just hold the idea gently. Imagine your reality, your entire universe, as a single, beautiful bubble floating in an endless ocean of other bubbles. It doesn't make our universe any less vast or wondrous. It just adds a layer of quiet, unanswerable mystery. A reminder that the totality of existence may be infinitely grander, infinitely stranger than what we can ever hope to see. And this leads us to an even more mind-bending idea, one that questions the very nature of the dimensions we experience. Is our universe a hologram? This is known as the holographic principle, and it is one of the most surprising and profound ideas to emerge from theoretical physics in recent decades. It suggests that all the information contained in a three-dimensional volume of space, like the room you are in, or the entire universe, can be described by a theory that lives on the two-dimensional boundary of that space. The idea first arose from the study of black holes. Physicists discovered that the maximum amount of information that can be stored inside a black hole is proportional not to its volume, but to the surface area of its event horizon. It's as if all the information about the three-dimensional things that fell in is somehow encoded on the two-dimensional surface. The holographic principle extends this idea to the entire universe. It proposes that our three-dimensional reality might be a holographic projection of information stored on a distant two-dimensional surface that surrounds us. What we perceive as depth, as the third dimension, might be an emergent property, an illusion created by the interplay of information on that fundamental boundary. This doesn't mean the world around you isn't real. The chair is still solid. The stars are still distant. It means that the way reality is coded at its most fundamental level might be radically different from how we perceive it. It's like watching a three-dimensional movie. The image appears to have depth, but all the information is stored on a flat two-dimensional screen. Is there any evidence for this? The idea is incredibly difficult to test, but some theoretical models have shown that a universe described by the holographic principle can reproduce features of our own cosmos, like the patterns in the cosmic microwave background. Some physicists even look for a kind of fundamental pixelation or blurriness in space-time, which might be a sign of its holographic nature. The holographic principle is a deep, and challenging concept, one that blurs the line between physics and information theory. But you can let the technical details fade away. Just rest with the poetic image it offers. Imagine that the entire universe, every star, every galaxy, every atom, every thought, is a magnificent, intricate hologram, a projection of a deeper reality written on a surface at the edge of time. In this view, reality is not made of stuff, but of information. And the world we experience is the beautiful, three-dimensional image that this information creates. It is a quiet and humbling idea that the solidity of the world may be a beautiful illusion, and that the true story of the cosmos might be written in a language of two dimensions, a story we are living from the inside. And if our universe is just one of many, or a projection of a deeper reality, then what about the rules that govern it? Are the laws of physics the same everywhere in every universe? The laws of physics, as we know them, gravity, electromagnetism, the quantum rules appear to be universal within our observable cosmos. A hydrogen atom in a galaxy billions of light years away behaves in exactly the same way as a hydrogen atom here on Earth. The speed of light seems to be the same everywhere we look. This uniformity is a cornerstone of science. It allows us to make predictions and to understand the universe as a coherent whole. But are these laws truly fundamental and unchanging? Or are they more like local bylaws specific to our particular corner of the multiverse? If the multiverse exists, it's possible that each bubble universe is born with its own unique set of physical laws. In one universe, gravity might be stronger. In another, there might be 4 spatial dimensions instead of 3. In yet another, the charge of the electron might be different, preventing atoms from forming at all. Most of these universes would be sterile and lifeless, unable to support any form of complexity. In this scenario, the laws of our universe are not special because they are the only possible laws, but because they are the ones that allow for observers like us to exist and ask the question. This is known as the anthropic principle. Even within our own universe, some have wondered if the laws could be subtly different in different regions, or if they have changed over time. We have no evidence for this, but it remains an open question. This idea challenges our most basic assumptions about reality. We tend to think of the laws of nature as eternal and absolute. But they may be more like the weather, a set of local conditions that just happen to prevail in our cosmic neighborhood. You don't need to decide which is true. Just feel the gentle release in the question itself. The rules that govern your world, the very laws that hold your body together, may not be the only rules there are. They may be just one beautiful, life-giving melody in an infinite symphony of cosmic possibilities. It is a thought that invites not certainty, but a deep and peaceful sense of wonder. As we drift deeper into the nature of physical law, we encounter one of the most astonishing and debated puzzles in all of science. It is known as the fine-tuning problem. Why are the universe's constants so perfectly set for life? The universe is governed by a handful of fundamental numbers or constants. The strength of gravity, the mass of the electron, the speed of light, the force that holds atoms together. These numbers are not predicted by our theories, They are simply measured. They are the dials on the cosmic machine. But what is so remarkable is that if you were to change any of these dials, even by a tiny, tiny amount, the universe as we know it would cease to exist. If the strong nuclear force were just a fraction of a percent, weaker protons and neutrons would not hold together, and atoms beyond hydrogen could never form. No stars, no planets, no chemistry. If it were slightly stronger, hydrogen would have fused into heavier elements so efficiently in the Big Bang that no fuel would have been left for stars to burn. If gravity were a little weaker, matter would never have clumped up together to form galaxies and stars. If it were a little stronger, stars would have burned out too quickly, collapsing into black holes before life had a chance to evolve. The list goes on and on. The balance is exquisitely and probably precise. The universe appears to be balanced on a razor's edge, perfectly tuned for the existence of complexity and life. So why? Why does our universe have this particular life-giving set of rules? There are several possible answers, each as profound as the question itself. One possibility is pure chance. We simply got incredibly lucky. The dials were set randomly at the Big Bang, and they just happened to land on the right numbers. To many scientists, this seems deeply unsatisfying. The odds are too astronomical. Another answer is the one offered by the multiverse. If there are countless universes, each with a different random set of physical constants, then it is no surprise that we find ourselves in one of the rare universes where the conditions are right for us to exist. We won the cosmic lottery, but there were a near infinite number of tickets. A third possibility is that there is a deeper, undiscovered theory, a true theory of everything, that shows these constants are not random at all. This theory would reveal that they must have the values they do for reasons of mathematical consistency. In this view, the universe is not fine-tuned. It is inevitable. We just haven't read the full instruction manual yet. And finally, some see the fine-tuning as evidence of design, a creator who set the dials with intention. While this is a question that lies beyond the realm of science, it is a natural response to the sheer improbability of it all. You don't need to choose an answer. Just rest with the wonder of the fact itself. The air you are breathing, the atoms that make up your body, the starlight that travels across the void, all exist because of a delicate, perfect balance. A cosmic blueprint that is so precise, so seemingly fortunate, that it has been called the greatest mystery of all. Our universe is not just a place of random chaos. It is a place of exquisite order. And this leads to a related question. We assume these constants are well constant, but are they? Have the physical constants truly remained the same throughout all of cosmic history? Most of our physical models are built on the assumption that the fundamental constants of nature do not change over time or space. The speed of light has always been the speed of light. The charge of an electron has always been the same. This assumption has served us well, and for the most part, our observations support it. But some physicists have wondered if this is truly the case. Could these constants have evolved in the early universe, settling into their current values, or could they be changing ever so slowly even now? Scientists have tried to test this by looking at the light from distant quasars. This light has been traveling for billions of years, carrying with it a snapshot of the laws of physics from a much earlier time. By analyzing the absorption lines in the quasar spectrum, which depend on the value of constants, like the fine structure constant, which governs the strength of electromagnetism, we can look for any changes over cosmic history. The results have been tantalizing but inconclusive. Most studies have found no change, but a few have hinted at the possibility that the fine structure constant might have been slightly different in the distant past. The measurements are incredibly difficult, and the potential for error is large, so the scientific community remains skeptical. But the question is a beautiful one. It challenges our idea of a fixed and eternal set of natural laws. What if the rules themselves are evolving? What if the universe is not just expanding and cooling, but also changing its fundamental character over the eons? It's like looking at a photograph of yourself as a child. You are the same person, but you have changed. Perhaps the universe is the same. The laws that govern it today may be just one phase in a much longer, more dynamic story. A story of a cosmos that is not just playing out a set of fixed rules, but perhaps in some very slow and subtle way is rewriting them as it goes. And what about the most famous constant of all? What determined the speed of light? The speed of light in a vacuum, denoted by the letter C, is the ultimate speed limit of the universe. Nothing with mass can reach it, and nothing at all can exceed it. It is a fundamental constant woven into the fabric of space-time. But why does it have the specific value that it does approximately 299,792 kilometers per second? Our theories don't tell us. Like the other constants, it is a number we measure. It emerges from the properties of empty space itself, the electric permittivity and magnetic permeability of the vacuum. But why do those properties have their specific values? The speed of light is not the speed of light. It is the speed of causality. It is the speed at which information can travel through the universe. It is what connects cause and effect. If it were infinite, every part of the universe could instantaneously affect every other part. If it were much slower, the universe would be a very different, more disconnected place. Some radical theories have proposed that the speed of light might not have been constant. In the very early universe, it could have been much faster, which would solve some of the same puzzles that cosmic inflation does. But again, we have no evidence for this. So as you rest, imagine this constant speed, a perfect, unwavering velocity that has been the same for billions of years. The light from the most distant galaxy travels at the same speed as the light from the lamp in your room. It is a universal rule, a cosmic speed limit that governs everything. And the reason for that rule, the reason for that specific number, is a mystery that is as deep as the universe is wide. It is the steady, silent pulse of causality beating at the heart of reality. Our journey now returns to a theme we touched upon earlier, but we will explore it more deeply. It is the great dream of physics, a quest that has captivated the greatest minds for a century, the search for a theory of everything. The universe, for all its complexity, seems to be governed by just four fundamental forces. The strong nuclear force, which binds atomic nuclei together. The weak nuclear force, which governs radioactive decay. Electromagnetism, which rules light chemistry and electricity. And gravity, which shapes the cosmos on the largest scales. For a physicist, four forces feel like too many. It suggests that there might be a deeper, more unified reality from which these four forces emerge. like different aspects of a single underlying principle. The history of physics has been a story of unification. In the 19th century, electricity and magnetism were shown to be two sides of the same coin, electromagnetism. In the 20th century, electromagnetism and the weak nuclear force were unified into the electroweak force. The dream now is to take the final steps, to unite the electroweak force with the strong nuclear force into a single, grand, unified theory, God. And then the ultimate prize to merge this unified force with gravity, creating a single, elegant theory that can describe every physical phenomenon in the universe. A theory of everything, but this has proven to be incredibly difficult. The energies at which the strong and electro-weak forces are predicted to unify are immense, far beyond what our current particle accelerators can reach. Unifying gravity is an even greater challenge as it requires reconciling the two different languages of general relativity and quantum mechanics. So is there a theory of everything we don't know? But the search for it is driven by a deep faith in the simplicity and elegance of the universe. A belief that beneath all the apparent complexity, there is a single, beautiful idea from which everything else flows. One of the most ambitious and famous attempts to create such a theory is string theory. Is it a correct description of reality? String theory proposes a radical and beautiful idea. At the most fundamental level, the universe is not made of point-like particles, but of tiny one-dimensional, vibrating loops of energy called strings. In this view, everything we see, an electron, a photon, a quark, is just a different vibrational mode of the same underlying string. It's like a cosmic guitar string. Pluck it one way and you get an electron. Pluck it another way and you get a photon. The different notes of the string are the different particles. The laws of physics are the rules of harmony. String theory is deeply attractive because in a single framework, it can accommodate all the known particles and forces, including gravity. One of the vibrational modes of the string naturally corresponds to the graviton, the hypothetical particle that carries the gravitational force. For the first time, this offers a way to describe gravity in a quantum mechanical language. But string theory comes with its own set of challenges. Its mathematics are incredibly complex, and for the theory to be consistent, it requires the existence of extra spatial dimensions, usually 6 or 7 of them, curled up so small that we cannot detect them. Furthermore, the theory doesn't make just one prediction. It allows for a vast landscape of possible universes with different laws, making it difficult to find a unique, testable prediction for our own universe. For decades, string theory has been one of the most active areas of research in theoretical physics. It has produced profound mathematical insights and has given us new ways to think about black holes and the early universe. But it remains a work in progress. We have not yet found any direct experimental evidence to confirm that the universe is made of tiny, vibrating strings. So as you drift, you can imagine this possibility: that the entire universe, from the light of a distant star to the substance of your own body, is a symphony, a grand and complex piece of music played on an orchestra of impossibly small, vibrating strings. We may not have seen the strings yet, but the search for their music, the search for that final unifying chord continues. It is a quest for the ultimate simplicity at the heart of existence. And this quest for unification leads us directly back to the problem of quantum gravity. What is its true nature? As we explored earlier, this is the central challenge of modern physics. How do we reconcile the smooth geometric world of Einstein's general relativity with the grainy, probabilistic world of quantum mechanics? String theory is one possible answer, but it is not the only one. Another leading approach is called loop quantum gravity. This theory takes a different starting point. Instead of assuming a smooth background of space-time in which strings vibrate, it proposes that space-time itself is built from quantum foundations. Imagine space-time as a piece of cloth. String theory is like studying the threads that make up the cloth. Loop quantum gravity is like studying the very weave of the cloth, the way the threads are looped and knotted together. In this theory, space is not infinitely divisible. It is made of discrete quantized chunks of volume woven together into a network of relationships called a spin network. Loop quantum gravity is a beautiful and mathematically rigorous theory. It naturally predicts that space is granular at the Planck scale, and it offers a picture of what might happen inside a black hole or at the Big Bang. Instead of an infinite singularity, there might be a big bounce where the universe collapses to a minimum size and then rebounds. Like string theory, loop quantum gravity is still a work in progress and has not yet been experimentally confirmed. Other ideas exist as well, each with its own unique approach. Causal set theory, which proposes that space-time is made of a discrete set of points linked by causality. Or twistor theory, which uses complex mathematical objects to try and reformulate the laws of physics. You don't need to understand the details of these theories. Just let the sense of the landscape wash over you. A landscape of brilliant minds exploring the very edge of what is known, each trying to find a path that connects the two great continents of modern physics. It is a search for a bridge between the world of the very large and the world of the very small. A search for a single story that can be told about both the atom and the cosmos. And in that search, there is a quiet and profound hope. Our journey now returns to the very first moments of existence, to a period of unimaginable energy and change. We have spoken of the Big Bang, but modern cosmology suggests that just a fraction of a second after the beginning, the universe underwent an even more dramatic transformation, a period of exponential expansion called cosmic inflation. But what drove it? The theory of inflation was proposed in the 1980s to solve several deep puzzles about the universe. One is the horizon problem. Why is the universe so remarkably uniform in temperature on large scales? The cosmic microwave background radiation is almost the same temperature in every direction we look. But in the standard Big Bang model, these distant regions would never have been in causal contact with each other. They couldn't have agreed on a temperature. Inflation solves this by proposing that in its first tiny fraction of a second, the universe expanded faster than the speed of light. This wasn't matter moving through space. It was the expansion of space itself. A region that was once infinitesimally small and in thermal equilibrium was suddenly stretched to astronomical proportions. This stretching would have smoothed out any initial irregularities, leaving the universe with the uniformity we observe today. Inflation also explains why the universe appears to be flat, and it provides a mechanism for seeding the structures we see. tiny quantum fluctuations in the early universe would have been stretched to cosmic scales, becoming the slight variations in density that later grew into galaxies and clusters. The theory of inflation has been incredibly successful. Its predictions match our observations of the cosmic microwave background with stunning precision. But the question remains, what caused it? The leading idea is that the early universe was dominated by a hypothetical energy field, which has been nicknamed the inflaton field. This field would have had a kind of repulsive gravity, causing space to expand exponentially. After a brief period, this field would have decayed, releasing its energy and filling the universe with the hot plasma of the Big Bang. But we don't know what this inflaton field was or why it had the properties it did. It is a placeholder in our equations, a name for a process we can infer but cannot directly see. Did it happen just once at the beginning of our universe? Or is inflation eternal? Some models of eternal inflation suggest that our universe is just one bubble that formed when inflation stopped in our region. But in the vast expanse beyond our bubble, inflation continues forever, constantly spawning new bubble universes. This is another path that leads us to the idea of the multiverse. The search for evidence of inflation continues. One of the key predictions is the existence of primordial gravitational waves, ripples in space-time generated by the violent expansion. Detecting these faint ancient waves would be a direct confirmation of inflation and would give us a window into the physics of the universe at energies far beyond what we can create on Earth. As you rest, imagine that first moment. A universe smaller than an atom, suddenly, incomprehensibly expanding. A brief, violent breath that set the stage for 14 billion years of cosmic evolution. The force that drove that breath, the inflaton, is a mystery, but its effects are written across the entire sky, in the smoothness of the cosmos, and in the seeds of every star you have ever seen. And this leads us to the structures that inflation seeded. How did the first supermassive black holes form so quickly? At the heart of nearly every large galaxy, including our own Milky Way, lies a supermassive black hole, millions or even billions of times the mass of our sun. We know that black holes can grow by accreting gas and merging with other black holes. But when we look at the very distant early universe, we see something puzzling. We find quasars, incredibly bright beacons, powered by supermassive black holes that already existed when the universe was less than 1 billion years old. Some of these black holes are already 1 billion times the mass of the sun. According to our standard models of black hole growth, there simply wasn't enough time for them to get that big. A black hole formed from the collapse of a single star would have to accrete matter at an impossibly high rate to reach that size so quickly. So how did they form? This is a major unsolved problem in astrophysics. One possibility is that the seeds of these black holes were much larger than we thought. The very first stars were thought to be extremely massive, and their collapse could have formed black holes hundreds of times the mass of the sun, giving them a significant head start. Another more exotic idea is the direct collapse model. In certain regions of the early universe, vast clouds of primordial gases might have collapsed directly into a massive black hole, perhaps tens of thousands of times the mass of the sun, bypassing the star formation phase entirely. These direct collapse black holes would have been born as giants and could then grow to supermassive status within the available time. Or perhaps there were other, more efficient ways for black holes to grow in the dense, chaotic environment, of the early universe. Maybe they grew in dense star clusters where mergers were frequent, or maybe they were able to pull in streams of cold gas along the filaments of the cosmic web at a much higher rate than we see today. The James Webb Space Telescope is now peering into this cosmic dawn, looking for the light from the first galaxies and the first black holes, hoping to find clues to this mystery. For now, these ancient giants remain a puzzle. They are like trees in a young forest that are already inexplicably ancient. Their presence tells us that the story of cosmic structure formation may have had a more dramatic, more rapid beginning than we ever imagined. They are silent, massive question marks at the heart of the first galaxies. As we drift from the puzzle of the first black holes, we find that even the galaxies they inhabit hold deep mysteries. What is the origin of galactic magnetic fields? We live in a magnetic universe. Our own Earth has a magnetic field that guides our compasses. The Sun has a powerful, complex field that drives solar flares. And on a much grander scale, entire galaxies, including the Milky Way, are threaded with vast, organized magnetic fields. These galactic fields are very weak, thousands of times weaker than the Earth's field, but they span tens of thousands of light years. They follow the spiral arms, they stretch out into the galactic halo, and they play a crucial role in shaping the galaxy. They guide the motion of cosmic rays, they influence the collapse of gas clouds to form new stars, and they may even help to drive galactic winds that blow material out into intergalactic space. But where did they come from? This is a long-standing puzzle. One possibility is that they were seeded by tiny magnetic fields in the very early universe, perhaps generated during cosmic inflation or other exotic processes just after the Big Bang. These primordial fields would have been incredibly weak. But as galaxies formed and contracted, the motion of the plasma within them could have amplified these seed fields through a process called a dynamo, similar to how the Earth's magnetic field is generated. Over billions of years, this dynamo action could have organized and strengthened the fields into the large-scale structures we see today. Another idea is that the fields were not primordial, but were generated later in situ within the galaxies themselves. The first supernova explosions and the jets from the first black holes could have created small-scale magnetic fields, which were then stretched, twisted, and amplified by the rotation of the galaxy. Telescopes that can observe the universe in radio waves are able to map the structure of these magnetic fields by looking at how they affect the light passing through them. These maps show beautiful, complex patterns, but they don't yet give us a definitive answer to the origin story. As you rest, imagine these invisible forces. Great silent rivers of magnetism flowing between the stars, shaping the galaxy in ways we cannot see. A force that is as fundamental to the life of a galaxy as gravity, but whose ancient origins remain a quiet cosmic secret. And just as galaxies are filled with these invisible fields, the space between them is not uniform. It is a vast tapestry of filaments and voids. Why are there these vast empty voids in space? When we map the universe on the largest scales, we see that galaxies are not distributed randomly. They are arranged in a magnificent web-like structure. They cluster together in long, thread-like filaments. And where these filaments intersect, we find massive superclusters of galaxies. But between these filaments are enormous, almost empty regions called cosmic voids. These voids can be hundreds of millions of light years across. They are not perfectly empty. They contain some dark matter and a few lonely galaxies. But for the most part, they are the great deserts of the cosmos. Their existence is a natural consequence of how cosmic structure forms. In the early universe, there were tiny variations in density. The slightly denser regions had more gravity, so they pulled in more matter, growing into the filaments and clusters we see today. The slightly less dense regions lost matter to their surroundings, becoming emptier and emptier over time. Gravity is a force that makes the rich get richer and the poor get poorer. The voids are the regions that lost out. While this general picture is well understood, there are still puzzles. Some observed voids seem to be larger or emptier than our simplest models would predict. And the subtle properties of voids, their shape, their temperature, the way they affect the light passing through them, can give us important clues about the nature of dark energy and the overall expansion of the universe. To imagine a cosmic void is to contemplate emptiness on the grandest possible scale. To float in the center of a void would be to see a sky almost completely dark, with the nearest galaxies just faint smudges of light on the distant horizon. They are places of profound silence and solitude, and yet they are not nothing. They are a fundamental part of the cosmic architecture, the quiet spaces that give shape and definition to the luminous web of existence. And from these quiet voids, we are sometimes startled by a sudden, brilliant shout from across the cosmos. What are fast radio bursts? In 2007, astronomers discovered a new and mysterious cosmic phenomenon. It was a single, intense burst of radio waves lasting only a few milliseconds that came from a distant galaxy. Since then, we have detected hundreds more of these fast radio bursts, or FRBs. Each FRB is incredibly energetic. In a thousandth of a second, it can release as much energy as our sun does in a day or even a year. And they are coming from all over the sky, from galaxies billions of light years away. What could produce such a powerful fleeting signal? This is one of the hottest mysteries in astrophysics today. The biggest clue we have is that some FRBs repeat. This tells us that at least some of them must come from a long-lived object, not a catastrophic one-time event, like a star exploding. The leading candidate for these repeaters is a type of object called a magnetar. A magnetar is a young neutron star with an unbelievably powerful magnetic field. Starquakes on the surface of these magnetars, or dramatic reconfigurations of their magnetic fields, could release enormous bursts of energy. We have even detected a weak FRB-like signal from a magnetar within our own galaxy, which strongly supports this idea. But what about the FRBs that don't repeat? These could be from magnetars that only flare once in a while, or they could be from something else entirely. Cataclysmic events, like the merger of two neutron stars, or a neutron star collapsing into a black hole, could also produce a single powerful burst. FRBs are not just a puzzle, they are also a powerful tool. As the radio waves travel across intergalactic space, they are affected by the sparse matter they pass through. By studying how the signal is dispersed, we can weigh the universe, measuring the amount of ordinary matter in the voids between galaxies. For now, every time a radio telescope catches one of these brief, enigmatic flashes, it is a reminder that the universe is still full of surprises. a quiet cosmos that every so often lets out a sudden, brilliant cry, a message we can hear, but whose language we do not yet fully understand. Our journey has taken us through the structures of the cosmos, both visible and invisible. Now, we drift into a more philosophical realm, to the very nature of the rules that govern everything. Are the laws of physics inevitable? Or are they just one possible set? The laws we have discovered, from Newton's gravity to the standard model of particle physics, are mathematically elegant and astonishingly powerful. They describe the universe with incredible precision. But could they have been different? This question brings us back to the fine-tuning problem and the idea of the multiverse. If our universe is the only one, then the laws of physics might be unique and inevitable, determined by some deeper mathematical logic we have not yet found. The constants of nature would have to have their specific values for the universe to be self-consistent. But if there is a multiverse, then the laws of physics might be more like local bylaws. Each universe could have its own set of rules, its own values for the fundamental constants. In this view, there is nothing special about our laws, except that they happen to be the ones that allow for complexity and life to emerge. This is a deep and perhaps unanswerable question, but it touches on our most basic assumptions about reality. Are the rules of the game fixed? Or did we just happen to land on a game board where we could exist? This leads us to a related mystery that has fascinated scientists and philosophers for centuries. Is mathematics an invention or a discovery? And why does it describe the universe so well? Mathematics is a language of pure logic and abstraction built from axioms and theorems. It seems to be a product of the human mind. And yet, time and time again, we have found that the abstract structures of mathematics provide a perfect language for describing the physical world. Einstein's equations for general relativity, born from pure mathematical reasoning, perfectly predicted the bending of starlight. The equations of quantum mechanics, full of strange and counterintuitive ideas, describe the behavior of atoms with flawless accuracy. It is, as the physicist Eugene Wigner called it, the unreasonable effectiveness of mathematics in the natural sciences. Why should this be? Why should a universe of matter and energy obey rules that can be described by the abstract logical constructions of the human mind? One possibility is that mathematics is a discovery, that mathematical truths are part of the fundamental structure of the universe, and we are simply uncovering them. In this view, the universe is inherently mathematical, and our minds have evolved to be able to perceive this underlying order. Another possibility is that mathematics is an invention, but it is an invention that has been shaped by our interaction with the universe. Our brains have evolved to recognize patterns, and mathematics is the ultimate language of patterns. We have created a tool that is perfectly suited to describing the world because it was built from our observations of the world. But this doesn't fully explain why purely abstract mathematical ideas developed with no physical application in mind so often turn out to be exactly what is needed to describe a new physical phenomenon years later. The relationship between the world of pure mathematics and the world of physical reality is a deep and beautiful mystery. As you rest, you don't need to solve it. Just appreciate the strange and wonderful harmony between the two. The universe seems to be written in a language a language of numbers and equations. And our minds, through some quiet miracle, have learned to read it. And this brings us to a modern frontier of physics where the line between matter, energy, and code begins to blur. What is the relationship between information and physical reality? In the 20th century, we learned to think of the world in terms of matter and energy. But in the 21st century, a third fundamental concept has come to the forefront: information. The physicist John Wheeler famously summarized this idea with the phrase, "it from bit." This is the proposal that the physical world, the it, emerges from information from bits. In this view, information is not just something we use to describe reality. It is the fundamental stuff of reality itself. We have already encountered this idea in several forms. The holographic principle, which suggests our 3D universe, could be a projection of 2D information. The idea of the universe as a quantum computer processing information over time. The black hole information paradox, which hinges on the principle that information cannot be destroyed. This informational view of the universe is a radical shift in perspective. It suggests that a particle's properties are not inherent qualities, but are the answers to yes or no questions. Is it spin up or down? Is it here or there? The universe, at its most basic level, might be a vast collection of these quantum bits of information. If this is true, it could change everything. It could provide a new language for a theory of everything. A language that could unite gravity and quantum mechanics by describing them both as processes of information. It could help us understand what happens inside a black hole, or even what consciousness is. This is a new and developing area of physics, and many of these ideas are still speculative, but they are also deeply compelling. Imagine the universe not as a great machine of gears and levers, but as a great thought, a vast unfolding piece of information. Every physical process is a transformation of that information. Every law of nature is a rule of that cosmic grammar. It is a beautiful and peaceful idea. It suggests that the world is not just a collection of inert stuff, but something more like a story, a message, a code that we as conscious beings are a part of. We are not just readers of the cosmic story. We are written into it. Our journey now takes us deep inside the heart of matter to the forces that hold it together and the strange states it can assume under the most extreme conditions. We begin with a puzzle at the core of every proton and neutron, the mystery of strong force confinement. The strong nuclear force is the most powerful force in nature. It is what binds quarks together to form protons and neutrons, and what binds protons and neutrons together to form atomic nuclei. It is the glue of the visible universe, but the strong force behaves in a very strange way. Unlike gravity or electromagnetism, which get weaker with distance, the strong force gets stronger as you try to pull quarks apart. The force between two quarks acts like a cosmic rubber band. The farther you stretch it, the harder it pulls back. The energy required to separate two quarks becomes so immense that it is more energetically favorable for the universe to create a new pair of quarks and antiquarks from the vacuum. These new particles then immediately bind with the original ones, creating two new pairs instead of two free quarks. The result is that we have never ever been able to observe a single isolated quark. They are permanently confined inside larger particles. This is known as color confinement. We have a very successful theory of the strong force called quantum chromodynamics, but we still cannot prove mathematically from this theory why quarks are always confined. It is an observed fact of nature, and our models work incredibly well with it. But the deep theoretical reason for it remains an unsolved problem. As you rest, imagine the heart of an atom, a tiny turbulent space where quarks are forever bound together by a force that refuses to let go. A force that grows with distance, creating a perfect, unbreakable prison. It is a quiet testament to the strange and counterintuitive rules that govern the very substance of your world. And what happens to this matter when it is pushed to the absolute limits of temperature and density? In our everyday world, matter exists as solids, liquids, and gases. But these are just the most gentle states of matter. The universe contains far more extreme environments. In the first microseconds after the Big Bang, the universe was so hot and dense that protons and neutrons could not exist. Instead, there was a seething soup of their constituent parts, free quarks and gluons. This state of matter is called a quark-gluon plasma. Scientists are now able to recreate this primordial state for tiny fractions of a second in particle accelerators, like the Large Hadron Collider, by smashing heavy ions together at nearly the speed of light. Studying this quark-gluon plasma helps us understand the nature of the strong force and the conditions of the infant universe. At the other extreme of density are neutron stars. These are the collapsed cores of massive stars where gravity has crushed matter so tightly that protons and electrons have merged to form a sea of neutrons. A single teaspoon of neutron star material would weigh billions of tons. But what is the exact state of matter inside a neutron star? Is it a superfluid of neutrons? Or does the immense pressure crush the neutrons themselves into a new, even more exotic state of strange matter made of strange quarks? We don't know. Neutron stars are cosmic laboratories of extreme density, but their interiors are hidden from our direct view. The questions continue. Can we create stable magnetic monopoles? Our experience tells us that magnets always have two poles, a north and a south. If you cut a magnet in half, you don't get a separate north and south pole. You get two smaller magnets each with its own north and south pole. But many theories of physics predict the existence of magnetic monopoles isolated north or south poles. The search for these hypothetical particles has been going on for decades, but none have ever been definitively found. The study of these strange states of matter is a journey into the heart of the possible. It is an exploration of the fundamental rules of existence pushed to their breaking point. It is a reminder that the world we see around us, the gentle world of solids, liquids, and gases, is just one calm shoreline on a vast and turbulent cosmic ocean of matter. Every story has an ending. As we drift toward the conclusion of our journey, we turn our gaze to the far, far future, to the ultimate fate of the cosmos. How will the universe end? The answer to this question depends on the delicate balance between the pull of gravity and the push of dark energy. For a long time, there were three main possibilities. If gravity were strong enough, it could eventually overcome the expansion of the universe. The expansion would slow down, stop, and then reverse. Galaxies would rush back together. The universe would get hotter and denser until everything collapsed back into a single point in a big crunch, a fiery mirror image of the Big Bang. If the expansion were just strong enough to overcome gravity, the universe would continue to expand forever. But the expansion would slow down over time, approaching a standstill. But the discovery of a dark energy has pointed us toward a different, colder, and quieter fate. Because dark energy is causing the expansion to accelerate, the most likely scenario is what is known as the heat death of the universe. In this future, the expansion will continue forever, faster and faster. Galaxies will recede from each other until the light from distant galaxies can no longer reach us. The sky for any observer in any galaxy will grow darker and emptier. Within each galaxy, the fuel for star formation will eventually run out. The last stars will be born, and then one by one, the existing stars will die. The massive stars will have long since exploded. The sun-like stars will fade into white dwarfs, glowing embers that will slowly cool over trillions of years until they become cold, dark, black dwarfs. The longest-lived stars, the small red dwarfs, will burn for trillions of years, the last faint night lights in a darkening cosmos. But they too will eventually flicker out. What will be left? A universe of remnants. Black holes, neutron stars, black dwarfs, and planets, all drifting through an expanding, near-empty void. It will be a universe of profound silence and cold, approaching absolute zero. But even this is not the final end. Over an almost unimaginable timescale, even these remnants will fade. Stephen Hawking showed that black holes will slowly evaporate through Hawking radiation. A supermassive black hole could take a Google years of one followed by 100 zeros to disappear. But eventually, it too will vanish in a final faint flash of particles. And what of the dead stars and planets? Some theories of physics predict that protons themselves are not truly stable but will eventually decay. If this is true, then over an even more mind-boggling timescale, all the remaining matter in the universe will dissolve into a thin soup of light and elementary particles. The final state of the universe would be a cold, dark, and empty void, with only a few stray particles and photons moving aimlessly through an ever-expanding space. A universe that has reached a state of maximum entropy where no more work can be done and nothing more can happen. A quiet, peaceful end. There is another more violent possibility called the Big Rip. If dark energy is not constant but grows stronger over time, the accelerating expansion could become so powerful that it overwhelms all other forces. First, it would tear apart clusters of galaxies. Then it would overcome the gravity holding individual galaxies together. As the end approached, it would rip apart star systems, then planets, and finally, in the last fractions of a second, it would become strong enough to tear apart atoms themselves, ripping the very fabric of reality to shreds. Our current observations suggest that the quiet heat death is the most likely scenario, but we do not know the true nature of dark energy, so we cannot be certain. You do not need to feel sadness at these distant cosmic fates. They are so far in the future that they are almost like fairy tales. Instead, appreciate the time we are living in now. We are living in the stelliferous era, the age of stars. The universe is young, vibrant, and full of light. It is a brief, beautiful morning in the long day of the cosmos, and it is a wonderful time to be alive. We have journeyed from the beginning of time to its distant end, from the vastness of cosmic voids to the heart of the atom. And for our final destination, we turn to the most intimate and perhaps the most profound mystery of all, the one that has been with us on this entire journey, the nature of consciousness itself. What is the role of the observer in the universe? This question brings us full circle back to the strange world of quantum mechanics. As we discussed in the quantum realm, the act of measurement or observation seems to play a crucial role. A particle exists in a cloud of possibilities until it is observed, at which point it chooses a definite state. This has led some physicists and philosophers to wonder if consciousness is not just a passive observer of the universe, but an active participant in creating reality. This is a radical and highly controversial idea. Most physicists believe that a measurement is any interaction with a macroscopic system, and a conscious mind is not required. But the question lingers. If the universe, at its fundamental level, is a set of probabilities, what is it that turns those probabilities into the definite solid reality we experience? Could consciousness be the bridge between the quantum world of potential and the classical world of the actual? This leads to even deeper and stranger questions. Could consciousness be a fundamental property of the universe, just like mass or charge? This idea is called panpsychism. It doesn't mean that rocks or electrons are thinking in a human way. It suggests that there is a primitive, simple form of experience, or proto-consciousness, inherent in all matter. The complex consciousness of the human brain would be an emergent property, a highly organized and sophisticated version of this fundamental quality. Panpsychism is an ancient idea that is finding new life as scientists grapple with the hard problem of consciousness. Why do we have subjective experience at all? Why does the firing of neurons in the brain feel like something? Why do we experience the redness of a sunset, the warmth of a fire, the feeling of joy? Physical science is very good at describing the structure and function of the brain, but it has no explanation for this inner subjective world. The hard problem is the gap between the objective physical world and the subjective world of experience. Perhaps we will one day have a complete physical theory of the universe, a theory of everything that can predict every particle interaction and every cosmic event. But can we ever have a truly complete theory without understanding consciousness? If consciousness is the very thing that is doing the observing and creating the theories, then how can it be left out of the picture? These are questions at the very edge of science, where physics, neuroscience, and philosophy meet. They are not questions that have easy answers. They may not have answers at all, but they are the ultimate questions. And as you lie here on the verge of sleep, you are at the very heart of this mystery. You are a conscious observer. You are a small piece of the universe that has woken up and is looking back at itself. And perhaps the greatest mystery of all is this: will we ever run out of questions? Every time we have answered a great question in science, we have found that the answer leads to a host of new, even deeper questions. We discovered atoms, and then we asked what they were made of. We discovered that the universe is expanding, and then we asked why it is accelerating. The more we learn, the more we realize how much we do not know. The circle of our knowledge expands, but the shoreline of our ignorance, the boundary between the known and the unknown, grows even longer. Perhaps this is the nature of a universe that is vast enough to contain consciousness. It is a universe that is endlessly explorable, endlessly mysterious. A universe that will always have a new horizon to drift toward, a new secret to whisper. And there is a deep and profound peace in that. It means that the journey of wonder will never end. Music swells gently, then fades to a softer, slower rhythm. And now, our journey through the great unsolved questions of physics comes to a close. We have floated through the silence before the Big Bang danced with the ghosts of dark matter and peered into the heart of a black hole. We have wondered at the perfect tuning of our reality and at the possibility of other worlds beyond our own. These questions are vast, but they do not need to weigh on you. Let them go. Let them dissolve like starlight in the morning sky. They are not yours to solve tonight. They are simply lullabies for a curious mind, reminders of the beautiful, intricate, and mysterious cosmos you are a part of. The fact that we can even ask these questions is the greatest wonder of all. That a collection of stardust on a small blue planet can look up at the night sky and question the very nature of existence. As you drift now into the quiet space between wakefulness and sleep, let your own consciousness be the final mystery, a gentle, warm, and private universe of thoughts, memories, and dreams. There is nothing more you need to understand, nothing more you need to do. Just rest. Let the questions of the cosmos fade into the silence, and let the quiet certainty of your own breath be the only answer you need tonight. Sleep well, and may your dreams be filled with wonder. Good night.